Jumping into talking about the periodic table today, how we organise elements. Some of this might be new, some of it might be old. Okay, success criteria. So this will help with some of that periodic table timeline, that you'll be able to fill in as we go, and otherwise it will be, I'll make sure you have access to the scan part of the textbook. So, outlining the development of the periodic table from about 1780 onwards to its current version that's on the front of your booklets. Identify the role that Antoine Lavoisier played in the development of the periodic table. State the meaning of d'Obereiner triads. Describe Mendeleev's process to develop his periodic table and why he left gaps. Compare and contrast Mendeleev's with our current periodic table. Identify groups and periods. Identify positions of metals and non-metals. Okay? All right. So this course focuses on the development of the periodic table from around 1780 and so on. I'll give you a copy of that text. But let's go through some of them. Antoine Lavoisier. Firstly, let's go back a little bit further to Robert Boyle, which is in your text, in part of that timeline, was in the 1600s. He revisited the definition of an element as a substance that cannot be broken down into a similar substance in a chemical reaction. Right? So that's why it's referred to as a pure substance. Around this time, only 12 elements were known. Do you want to have a guess at what some of those might have been?
Carbon.
Carbon? Yeah. Oxygen? No. No, not gases.
Gold.
Yeah, gases came later. Gold, yeah.
Silver.
Lead, silver, copper, yeah, right? So particularly our unreactive metals that exist as their pure form in nature. So things like salt, sodium chloride, sodium was discovered way later because it's a reactive metal, yeah? Gases, many are odorless and they're colourless. So we didn't know much about gases, right? Until Lavoisier came along. So 1700s, we're up to about 33 elements. Many of those elements were actually compounds, but lacking equipment and technology and the means to be able to isolate them further. Right, best known in his work for the discovery of the oxygen's involvement in combustion and the development of the law of the conservation of mass. And we'll explore that in more detail in our next unit. Yeah, so topic 2 on chemical reactions. d'Obereiner's triad. Tri means 3. So d'Obereiner, Johann Wolfgang d'Obereiner, late 1700s, early 1800s. This idea about triads, and what he found was there were these groups of 3 elements that had similar chemical properties and physical properties, right? So alkali forming elements, alkali is a base, right? So when these elements react with water, they form a basic solution, lithium, sodium, potassium. Alkaline earth-forming elements. So similarly reactive, but not as reactive as the alkali metals, calcium, strontium, barium. Salt-forming elements. So these are halogens that we knew them to be later, are gases that react quite readily with the alkali metals to form salts. And we'll talk about salts when we, at the start of next term, when we look at ionic compounds, which is what many salts are. Acid-forming elements, so sulfur, selenium, tellurium, right? All of these are in group 16. When they react with water, sulfur goes to sulfuric acid and so on. They're also very smelly compounds. They're known as the chalcogens, but you don't need to know that. And then iron triads. So I guess linking this idea about iron and similar like metals to iron, cobalt and nickel. They're actually not in the same group. They're in the same broader group called the transition metals, and we'll talk a little bit about those, but not too much. Mendeleev, right? So 1863 of the known elements, 56 were known. And then he developed them according to a pattern of increasing atomic mass and periodic valency. So valency we know as to be valence is the valence or outer shell electron. Periodic means reoccurring. Yeah? And then by atomic mass. And so what we notice is that hydrogen's 1, helium's 4, boron is 8. And so as we double the mass, we see this periodic trend. And so we can see that there are what he referred to as a series or a periodic series, and then looking at 8 main groups. And so this idea of this recurring trend. Oh, what happened there? So slightly prior to Mendeleev, which is in your worksheets, was a guy by the name of John Newland. Yeah, came up with this idea of the law of 8, which he likened to a musical octave. And many of his peers, for referring to it as music, he was largely discredited, but very well, I guess historically now well respected. Oh, the main thing about Mendeleev is he left gaps, right? So he found this recurring trend, but because not all elements were known, right, obviously there were gaps in his trend. So he's like, oh, there must be an element that exists here. So for the following 90 years, right, until 1943, when the last piece of the puzzle was placed in, element technetium, right, the last piece of the puzzle of the naturally occurring elements in 1943, I believe. No, 1953? Anyway, don't remember exactly, but in the 1940s or early 50s, last piece of the natural occurring elements were found out. So leaving gaps, and it's these reactive and other metals that exist as compounds in nature that were then isolated. It was also from the early 20th century when we started getting electricity and better cooling technologies that we were able to use a form of distillation to cool the air, and we were able to isolate nitrogen, oxygen, and argon from the air. Okay, the modern periodic table are based on atomic number, not atomic mass. And what we knew from our last topic we looked at, atomic number equals to the number of protons. We don't refer it to by mass because there are certain locations where the average mass of the next element is slightly lower. So argon has a mass of, I think, 40, whereas potassium only has a mass of 39. And that relates to its abundance of stable isotopes that are lighter. So atomic number rather than atomic mass. So here's our side-by-side comparison. Mendeleev has 12 rows, modern only has 7, which we call periods. Periods refer to the number of electron shells. Mendeleev had only 8 columns or groups. We now have 18, with that middle 10 elements in the middle called the transition metals. Mendeleev obviously had gaps, and the modern has none. Mendeleev had some element groups with differing properties, modern groups with all similar properties. So all group 1 metals have similar properties. All group 2 have similar properties, and so forth. The exceptions you'll notice is hydrogen is sort of a group 1 metal in that it's got 1 electron in its outer shell, but it's also sort of like a group 4 or 14, right? But in that it's a half-filled shell, being that first shell can only have 2 electrons. So it's a bit special in that sense. Mendeleev does not support the idea of isotopes. Remember, isotopes have a different atomic mass, right? So, because neutrons weren't discovered until the 1830s. So we're looking 60 years beyond his periodic table. And it was neutrons that accounted for why we had these differences in there. So modern obviously supports the idea of isotopes, owing to not ordering by mass number but by atomic number. And we know that the masses that you can see on your periodic table provided, some of them have 0.9 or 0.5 or 0.3. And that's because it's the weighted average of all the different isotopes together. Lastly, Mendeleev lacks the support for atomic structure. Modern, we can deduce the electron configuration based off its location. Okay, so we think about protons. Electrons weren't discovered until 1906, but protons shortly thereafter. Electrons shortly thereafter, protons after that, neutrons after that. So we're looking at 1896 was sort of the idea of an atom, 1906 electrons, 1917 is the proton, and 1932 thereabouts was neutrons. Don't need to know that too much, but this idea of just to get an appreciation for the development of periodic table over time. Groups and periods. Groups signified by vertical columns. We're mainly going to be looking at what's called the main group metal, main group elements, which is 1, 2, 13 through 18. And periods, right, are the rows. So 1 through 18, 1 through 7. Notice how these two rows at the bottom, they actually fit in here. So if you notice the atomic number jumps from 53 to whatever it is, 68 or something like that in period 6, similarly for period 7. Metals. Metals form most of the elements in the periodic table. Notice from this element here, boron, that we have this staircase that goes down. And what this staircase, they're called the metalloids, and it's the transition, right? It's the blending of metals and non-metals. So metals are generally lustrous. That means they reflect light. They're good conductors of heat and electricity. We'll talk about metals in greater detail later in the year. They're high density, meaning that the particles are closely packed. They have high melting and boiling points, which means the bonds holding it together are strong. They're ductile and malleable, which means they can be changed easily into shape without it being broken. So we expect if that's the metals, then the non-metals have the opposing properties. So instead of being lustrous, they're dull. Instead of being conductive, they're not. Instead of being malleable, they're brittle. Instead of being they're lower in density. They're lower in melting and boiling points. And then our metalloids, therefore, are going to share, right? They're generally solid, but they might be a bit brittle. They can be lustrous or dull. They can be somewhat conductive. Silicon, for example, is known as a semiconductor. So it's not that great a conductor, but it will conduct a little bit. Certainly not as good as metals, and so on. So there we go. That finishes off for that part. So on to the timeline.